Hello everyone, and welcome to the last section in Module 4, 1.7, where we'll look at inequalities. I don't know, if you looked at the learning guide at all, I have no idea what this front page thing says. Something about being in love and explaining, I don't know. I tried to make sense of it, but it seems kind of crazy to me. So we'll just get started on the problems. So let me kind of give you a crash course on interval notation. It's actually not that bad. So once we get this, everything will be kind of straightforward. So interval notation. It's basically a way to compactly describe values on the number line. So if you have a compound inequality, something like -2 less than or equal to x less than, let's say, 5. We could graph this, and the way you graph it is you just draw the number line. You find the important values, -2 and 5. And then what I normally do is I do a shaded dot if it can equal the number, and an open dot if it can just get close to the number. So these would be our values. In the book, they shade a little differently, but the interval that this corresponds to is a square bracket and an open parenthesis. And I kind of think of these numbers as bookends. The smaller number always comes first. In the book, they shade a little differently. I like to shade above just because it's clear, and I'll maintain this for the rest of the video. But on my math lab, when you're answering questions, they would do it like this. And they would actually take the interval symbol and they would say, okay, it goes from here to here, and then they would shade. I think it's a little bit harder to draw that way, so I will stick with these three methods. But that's basically how the interval works. There's a few other things you want to have a handle on if you're using this interval notation. Say we have an inequality, say x less than 7. How do we solve something like that? Or we don't need to solve, it's already solved for. But graphically, you'd have a 7. It would be all the numbers smaller, so to the left. But how do you get the interval? Well, the smallest number, it has no smallest number, so we put a negative infinity. And negative infinities always get parentheses, because you can kind of never get there. There's no number that's the same as infinity. There's always something smaller. And for instance, if you would have another one with, say, x bigger than -2, the graph would be similar. You would just be shading to the right. Let's make this greater than or equal to, so we get used to both notations. So -2 would be here, shade this dot, and graph to the right. We'd have -2, and then no biggest number, so we do positive infinity with an open parenthesis. And that's basically interval notation. When you have multiple sets, sometimes we'll look at how to join two sets of numbers. And there's two ways to join two sets of numbers with this interval notation. We'll have like the union, and we'll also have the intersection. And they both have special symbols. So the union is represented with the U, or in words, it's or. And intersection is represented by this upside down looking U. And in words, this is the mathematical word and. Okay, so the union is basically all elements in either set. And intersection is only elements common to both sets. So let's take a look at how something like this might happen. Well, you could have a complex thing, and we'll see this is where the language will come in, say like x less than -2 or x bigger than 1. Well, graphically that would look like this. We'd have -2, open dot to the left, and we'd have +1, open dot to the right. And then basically we'd do each interval, so we'd have negative infinity up to -2, and this one would be a 1 up to positive infinity, and we'd just join them with a U. The OR means we want all the elements common to both sets, the one going left and the one going right. If we had an intersection, though, say we had something like x less than 4, less than or equal to 4, and we'll say x bigger than 1. What's going on here? Well, let's maybe use some colors. Is it easy to use colors on here? Yeah, let's say we have, I don't know, I'm colorblind, so this might be terrible. Let's say we have 4. Okay, so we have 4 somewhere up here. Shaded dot, because it's the numbers less, and then we want to do the ones that are bigger than 1. So we have 1 somewhere down here. I don't know if that's blue or purple. I'm so colorblind. We have a open dot here, and we shade to the right because it's the bigger numbers. And so if the ones are shaded red and the ones are shaded blue, then the ones that will be common are the ones that are shaded both colors. So what that means is the intersection is going to be 1. Notice 1, we're going to do an open parenthesis because it is not actually colored blue or purple, whatever that is. There's an open dot there, but that's where it gets started, and then it goes all the way up to the 4, and that's the last number colored both things, so that one gets a bracket. And that's how you do intersection. Okay, so let's get back to the worksheet and actually finish the actual problems there. Okay, so express 1/6 in set builder notation and graph. Set builder notation is just the inequality, but there's like a fancy little bracket x bar, and then we do the inequality. This literally just reads x such that, that's what the bar stands for, and then we actually do the inequality. So here it would be 1 less than x, and then it can actually equal 6. So x such that 1 is less than x is less than or equal to 6. And then graphically that would look something like 1, I do an open dot, up to 6 with a closed dot, and then shade in between. It's a little bit harder for me to draw it like this, but you see what I mean. Instead of here they have less than or equal to, and it gets the square bracket, and here we have strict inequality, and it gets an open parenthesis. Okay, so set builder notation here, nothing too fancy. This is just x such that -3 is less than or equal to x is less than, oh, and that's all we need to do. We don't need to do less than because it's infinity, which means it keeps on going. So let me erase that and just close up the square brackets. So on the graph, these are just the numbers bigger than or equal to -3. Okay. So to find the intersection, here's another one. So that, remember this symbol means intersection. So make a mental note until you get practiced up. So we want to graph both of them and find which ones are both. So we have a -3, -1, 0, and 2 that are important. -3, -1, 0, and 2. It's not too important if you do these to scale. We're just trying to see where they intersect. So we have -3 to 0. This one's open to open. And then this other one, -1 to 2, they're actually both shaded. So what are the ones, if you imagine they're two different colors that are colored both, we'd get this region right here from -1 up to 0. That's what our intersection would be. So -1, 0. The union, that just includes both of them. So let's do this. Smallest number is -3. Then we have a 0. We have a -1, a 0, and a 2. So one set is -3 to 0. And another set is -1 to 2. And basically we're just going to go from one end to the other. All the elements in one set or the other. So this is going to be our union, the line I drew below, which will be -3 to +2. Okay, so now we'll actually talk about solving inequalities. So to solve an inequality, everything works the same as an equation. So you can add things to both sides, subtract things to both sides, multiply things to both sides. But the only thing is when you multiply or divide by a negative value, the inequality flips. So that's one really important thing. So multiply or divide by a negative. We need to remember to flip the direction of the inequality. So in this one, to get x alone, we divide by -9, but then we have to flip the symbol. So if the alligator's mouth opens to the left now, after we multiply by a negative, it'll open the other direction. So these are the values x less than -4. And to make sure that this operation makes sense, just plug in some values into the original equation. For example, an x value less than -4 is -5 in the original equation, or inequality. -5 times -9 would be +45, which would indeed be greater than 36. And it says graph. It doesn't say anything about doing the interval, so we'll just graph it quickly. So this is -4. We want the number smaller, so we go this way. Okay, solve and graph on a number line. Again, nothing too complicated. We remember from earlier modules, we just want to get rid of fractions. So start by multiplying everything by 4. I think somehow they meant to have an inequality symbol here because equals just gives a regular number. So just for the sake of making this more fun, let's pretend that's not equals. Let's say it's greater than or equals, like that. So if we multiply 4 by x over 4 minus 3 over 2, and then greater than or equal to x over 2 plus 1, and we need to multiply that by 4 also. So when we distribute the 4, we'll get x minus, and then 4 times 3 over 2 is going to be 12 over 2, or minus 6, greater than or equal to. 4 times x over 2 is 2x, and then 4 plus 1, 4 times 1 is positive 4. So if you move the x to the right, so first start by subtracting x. So we have -6 greater than or equal to x plus 4. Then just subtract 4. So here we'll have x less, or yeah, -10 is greater than or equal to x. So we have our number line, we have -10, and x is all the numbers smaller than or equal to that. Just for refresher for interval, that would be -infinity up to -10 with a square bracket. Okay, get some word problems here, so let's see how this goes. An elevator at a construction site has a maximum capacity of 3,000 pounds. If the elevator weighs 245 and each cement bag weighs 95, how many pounds of cement can safely be lifted on the elevator in one trip? Okay, so basically we know from the problem we have a certain amount of weight and it needs to be less than or equal to 3,000. What is affecting our weight? Well, we've got the static weight of the employee that weighs 245 pounds, and then he has a certain number of cement bags that he's bringing with him. So basically, let's just let x be the number of cement bags. It's always good to identify the variable. So each bag weighs 95, so the weight it will contribute will be 95 times the number that he brings. And then this will figure out, if we solve for x, what the largest number of bags he can bring is. So start by subtracting 245 from both sides. So we have 95x less than or equal to, looks like 2755 to me. Then divide by 95, and we'll see the maximum number that he can bring. Okay, so I need to use the calculator for that, I do believe. Alright, so 2755 divided by 95 gives 29. So the largest number of bags he can bring safely is, did it say 27? Yeah, 29. So 29 bags is the most he can bring. So 29 bags puts the elevator at capacity. Okay, so let's do a few more inequalities. 4a and 4b are very similar. Sometimes you can get something that's true or false, which is basically what they're trying to show here. That's why you can get something so complicated. So basically this works like equations. Just multiply everything out and see what you get. So distribute the 4. 12x minus 8 minus 3x less than 3 plus 9x, distributing the 3 minus 7. Now we combine like terms, so we get 9x minus 8 is less than 9x minus 4. Take away the 9x. Negative 8, is that less than negative 4? Sure is. So this is always true. So the solution set is all real numbers. Or we can specify it as the whole number line, which would be from negative infinity all the way up to positive infinity. All right, try the next one. First distribute the 5, then the negative 3, and start combining stuff. So 5x minus 10 minus 3x minus 12 greater than or equal to 2x minus 20. So we get 2x minus 22 bigger than or equal to 2x minus 20. If we subtract 2x from both sides, we'll see that we end up with negative 22 greater than or equal to negative 20, which is not true. Negative 20 is smaller, so this is false. So the solution set, so no solution, or that we say the solution set is the empty set. That's what the symbol represents right here that they're using over here. If we haven't discussed it, the empty set just stands for the set with nothing in it. Okay, let's do a couple more. So compound inequality, nothing special. The only rule of thumb here is if you do something to one part, you have to do it to all three. So let's start by adding 1. So we have to add 1 to all 3 parts to try and get the x by itself. So we get negative 10 less than 2x less than or equal to negative 4. Then divide all 3 parts by 2. So we get negative 5 less than x less than or equal to negative 2. Or in interval notation, negative 5 up to negative 2. Okay, so a couple with absolute values. Important thing to note here is that there are basically 2 scenarios, so I will explain those now. So if we have absolute value inequalities, basically there are 2 big cases. If you have the absolute value of an algebraic expression less than a number, then that's going to force that algebraic expression to be between the negative value of the number and the positive value of the number. So in order to solve the absolute value inequalities, we need to find a way to take away the absolute value. And the other scenario is the absolute value of the algebraic expression being larger than the number. Then you'll end up with the algebraic expression less than the negative value of the number, or the algebraic expression greater than the number. So I know that seems kind of cheesy, but it'll just help you realize how to apply these with algebraic expression rather than numbers. But some basic examples, say we have the absolute value of x less than 5. Well, the only way that's going to happen is if your numbers are trapped between positive 5 and negative 5. All those values. Why is that? Well, pick something over here to the left. X equals negative 6. When you take the absolute value, it's positive 6, which is too big. And same with anything over here. Think about the absolute value of x being bigger than, say, positive 3. Well, the only way the absolute value is going to be bigger than positive 3 is if it's the other part. So you have negative 3 to 3. You have the same sort of region, but now we're going the other way. All the numbers in between will be too small. For instance, absolute value of negative 2 is positive 2, which is not bigger than 3. But if you look at the absolute value of negative 4, it's positive 4, which is bigger than 3. So you need to use these two rules when we're solving absolute value inequalities. So it might be helpful to note that. All right, so this one we have the absolute value of an expression less than a number. So that means we do negative 8 less than the expression less than the number. And then we solve this. So add 6. And we get negative 2 less than 2x less than 14. And then divide by 2. So we have negative 1 less than x less than 7. Or negative 1 comma 7. Remember that's an interval, not an ordered pair. You always can only tell based on the context of the problem because it does look very, very similar. All right, let's look at this inequality. This is the same one, so same process. So I'll actually skip over this one now. I'll just show you the first step. So you would do negative 8 less than or equal to 2 times x minus 1 plus 4 less than or equal to 8. And then you just continue in the same way as before. So you have an algebraic expression less than or equal to a number. Here is one where it's a little bit different, right? We have the algebraic expression being bigger than the number. So if you picture it, it needs to have absolute value bigger than 1. So that will happen if 2 minus 3x is smaller than negative 1, or 2 minus 3x is bigger than 1. So now we need to solve both of them, and remember that or turns into a union when we do the interval notation. So start by subtracting 2, so you have negative 3x less than negative 3, or over here we subtract 2 also and get negative 3x bigger than negative 1. So now in both these we're going to have to divide by negative 3, but remember to flip the symbols. Got to flip the symbols. So here we have x bigger than positive 1, or x smaller than positive 1/3. So this part is 1 up to infinity. We union that with negative infinity up to 1/3. And that's it. So hopefully you enjoyed solving these inequalities as much as I did. And good luck on the homework and the test. All right, see you next module.